Hello and welcome to our next lecture. Today we're talking about a real Fourier series, as opposed to the complex Fourier series that we talked about in the previous one. The complex Fourier series have one glaring issue: they're complex. But if we want to represent the real valued functions, then the complex valued Fourier series seems a little bit like an overkill. We'd like to represent real valued functions with real valued series. And there is a way to do that by representing the exponential terms with sines and cosines instead. If you remember, the functions e to the I omega t can be represented as combinations of sines and cosines. This can be written as a cosine of omega t plus I sine of omega t. Hence, it might be a good idea to use cosines and sine instead of the complex valued exponentials. So the proposal is the functions cosine omega in my Fourier series were 2 pi k over b minus a t, and the function sine of 2 pi k over b minus a t. There's only one function that's missing from this set. It's the function 1. Because when omega is 0, or when k is 0, cosines and sines don't really represent it. Yes, we can assume that the cosine will allow k to be 0, but then inside the sine, k equals 0 makes it a 0 function. So traditionally people say that k goes from 1 to infinity for both sine and cosine, and the function 1 is just included as a special addition to this basis set. In your homework, you found out that these functions are indeed orthogonal. The only problem is orthogonality to 1, but it's not really that big of a deal because the cosines and sines both integrate into 0, and therefore their inner product with the function 1 will be 0 anyway. So I'd like to talk a little bit about how you compute the coefficients. Suppose that we are given a function f from the set L to a to b. Then we compute the projection of f on the function 1 by computing the coefficient a naught, which is going to be the inner product of f with the function 1 divided by the inner product of 1 with itself. The inner product of 1 will depend on the interval a to b that we're talking about. Then we'll also compute the coefficients of the projections of f onto cosine. I'm going to call that ak, will be the inner product of f with the function cosine of 2 pi k over L, where L is the b minus a, divided by the norm of cosine of 2 pi k over L t squared. And the coefficient bk will be the inner product of f with sine of 2 pi k over L t divided by the norm of sine of 2 pi k over L t squared. Expressing inner products as integrals, we get that a naught is going to be the integral from a to b of f multiplied by 1, so it's just f of t dt. And the norm squared of the function 1 is just going to be b minus a, and therefore it's just 1 over L right here. ak is going to be the integral from a to b of f of t times cosine of 2 pi k over L t dt. The norm of the cosine, as you have computed in your homework, is L over 2, so it's just going to be 2 over L. And the coefficient bk is going to be the integral from a to b of f of t times sine of 2 pi k over L t dt. And again, the norm of those functions is L over 2. Therefore, it's going to be 2 over L in front of the integral. Taking all of this into consideration, we have the following theorem. That the set of functions 1 cosine of 2 pi k over L t sine of 2 pi k over L t, where L is b minus a, form a complete orthogonal set in L2 a to b. By complete orthogonal set, I actually mean a basis that can represent every possible function from L2. The completeness is the bit that I didn't prove, but again, I'm going to swipe the details under the rug and say that this is true, that these functions make a complete orthogonal set. As examples of computations of real Fourier series, I'd like to turn to my favorite functions, the tanh function and the step function. So again, I consider both of those functions to be elements of L2 from -1 to 1. So for the function f, we have that a naught is just the integral from -1 to 1 divided by 1/2, because L is 2, the integral of f of t times 1 dt, and that integral is simply 1/2 times 1, it's just 1/2. The coefficient ak can be computed as 2 over L, which is 2, integral from -1 to 1 of f of t, which is my tanh function, times cosine of 2 pi k over L, which is 2 t, which I can write as 2 times the integral from 0 to 1, because both cosine and f of t are symmetric. So this is just going to be 2 times the integral from 0 to 1 of the function 1 minus t times cosine of pi kt dt. So it's the same function f of t. Let's integrate the function f of t with the function cosine of pi kt for t from -1 to 1. Well, knowing that the cosine of k pi is either +1 for even k or -1 for odd k, we can say that this is going to be 2 minus 2 times -1 to the power k over k pi squared. Just to show you that my other integral is also correct, I'm going to do that one as well. So instead of integrating from -1 to 1, I'm going to integrate from 0 to 1 and multiply by 2. And the result is exactly the same. bk is going to be 2 over L, the integral from -1 to 1 of f of t, times sine of 2 pi k over 2 t dt. I do know that f of t is an even function and sine is an odd function, so the product of the even and the odd function is going to be odd function. The integration of the odd function over a symmetric interval, such as -1 to 1, is going to be always 0. Changing cosine to sine, gives us 0. I added the assumptions because without the assumptions option, the integrate command would assume that k might be a real value, and therefore we can actually have a non-zero integral. So it looks like f of t can be written as 1/2 plus sum k goes from 1 to infinity. The coefficients ak are 2 minus 2 power minus 1 to the power k over k pi squared times cosine of 2 pi k t over 2, so it's just pi k t, plus 0 times sine of pi k t. Let's see if that works. So I'm going to define f as a summation. First, I add 1/2, so it's just there. 1/2, the coefficient is this. Of cosine of pi kt, and let's add k from 1 to, I don't know, 10 terms. And let's plot f from -1 to 1. And here we go. If I add more terms, the representation will be slightly more accurate. And just as before, yes, this Fourier series makes the function repeats itself many times. Outside of the domain of the space L2, Fourier series, both complex and real, assumes that the function repeats itself. Let's talk about the function g. Coefficient a0 is just going to be 1 over L, the integral from -1 to 1 of g of t times 1 dt. Very easy to see that both halves of the function g will cancel each other out, and we're going to get a zero integral. ak is going to be 2 over L, the integral from -1 to 1 of g of t times cosine of pi kt dt. I do know that g of t is odd, cosine is even, the product of the even and odd function is going to be odd, and this integration is just going to be 0. bk is going to be 2 over 2, the integral from -1 to 1 of g of t times sine of pi kt dt. This product is going to be even, so if you want to simplify it, then we can just say that this is 2 times 2 over 2 is 1, integral from 0 to 1, g of t on 0 to 1 is 1, times sine of pi kt dt. This integral is quite easy to compute, so I'm just going to do it. So it's 2 times the integral of pi kt is 1 over pi k times negative cosine of pi kt evaluated from 0 to 1. So at 1 we get cosine of pi k, so we get minus cosine of pi k minus, when t is 0, cosine of 0 is 1, so it's -1. So we simply get 2 times 1 minus cosine of pi k over pi k. Let's see if we get a similar result with Mathematica. If I integrate g of t from -1 to 1, I get 0. That's expected. Now let's try to integrate with the cosine of pi kt. we get 0. What about sine? This is what we get. That's exactly the answer we've got. So what if I try to do two integrals from 0 to 1? Again, it's exactly the answer I've got. So now all I need to do is to reconstruct my function. This time the coefficient a0 is 0. And I get 2 minus 2 negative 1 to the power k. That's still the same, except that we have k pi in the bottom, and then that's only the sine functions are actually playing the role. And this result is quite similar to the complex Fourier series that we computed before. You might be wondering, maybe there is a connection between the two, and yes, there is a connection between the two. If I add more terms in this summation, I get a slightly better representation of my step function, but I get those unknown jumps at the endpoints. So in a way, the series is 0 plus the sum. K goes from 1 to infinity. The coefficients a, k are 0 times cosine of pi k plus 2 times 1 minus cosine pi k divided by pi k multiplied by sine of pi k t. We can compute Fourier series for many functions. So let me demonstrate how it can be done for just a random function. So let me define a function h that is t e to the minus t, and assume that this function lives in the space from 0 to 2. So let's compute the Fourier series for this function. A0 is just going to be the integral of h of t when t goes from 0 to 2 times 1 over L. AK is going to be 2 over L times integral of h of t times cosine of 2 pi k over L, which is 2 in this case, multiplied by t, as t going from 0. Let's replace 0 with a and b. And let's just say here that a is 0 and b is 2. And let's plot this function from a to b. The reason I do that is that I'm going to show you how this changes a little bit when we change a and b. That's a quite big formula, but Mathematica will have no problems dealing with that. So a0 is going to be a over b minus a. 1 over b minus a. This will have to be 2 over b minus a. And this will also have to be 2 over b minus a. Gotta integrate h of t times sine of 2 pi k. And again, this would have to be b minus a as well. Sine of 2 pi k over b minus a t as t going from a to b. Let's add a few terms. So it's just going to be a naught plus sum, and then we'll have ak times cosine of and bk times sine. And let's run the sum k going from 1 to, let's just add a few terms. Let's plot it from a to b. And here we go. Well, that doesn't look like our function, but if I add a few more terms, then the plot will look a little bit better. Notice that the plot has a little bit of a jump right there at the end, and it seems like on the other side it starts from exactly the same position. It's because our graph, when it's repeating itself over and over, then there is a jump between the end point here and the start point of the next repetition. And so the Fourier series tries to connect the end of the function to the beginning of the next repetition. Suppose I change b to something like 5. Well, the function looks a little bit different. We'll need to recompute all of the coefficients. I will recompute the sum, and we'll do the plot. The plot is actually quite nice. It represents the function quite nicely. Yes, it also has repetitions of the function, and yes, the repetitions of the functions are creating these ripple kind of effects of the discontinuities. But it seems like Fourier series represents the function quite nicely. If I include more terms, then we probably won't be able to tell the difference, except that there is this little ripple at the end. The last thing I want to talk about today is that there is a connection between the complex Fourier series and the real Fourier series. You remember that we can represent the function f of t as a summation of c naught plus the sum, and I'm going to let k go from 1 to infinity. And the complex Fourier series had ck e to the I omega k t plus c negative k, because their series was running from negative infinity to positive infinity, so both positive indices and the negative indices were present. So what I'm doing here is I'm just reordering the summation a little bit. So this is just c naught plus the sum. K goes from 1 to infinity. Ck, it was e to the I 2 pi k over L t plus c minus k e to the I 2 pi negative k over L t. If I use the earlier formula, then c naught stays c naught. Ck will be multiplied by cosine of 2 pi k over L t plus I sine of 2 pi k over L t plus c negative k multiplied by cosine of minus 2 pi k over L t plus I sine of minus 2 pi k over L t. Cosine is the even function and sine is the odd function, so I can write it as c naught plus sum k goes from 1 to infinity, and then for the cosine I have ck plus c minus k multiplied by cosine of 2 pi k over L t. But for the sines I have the following. I have I, and then I have ck minus c negative k multiplied by the sine of 2 pi k over L t. So what happens here, if I compare it to the real Fourier series, which has a coefficient a naught plus the sum k goes from 1 to infinity of ak cosine plus bk sine, then I can tell that a naught should be the same as c naught, and ak should be ck plus c negative k, and bk is I ck minus c minus k. We can use this relationship to solve for the coefficient ck. So c naught will be the same as a naught. So if we have a real Fourier series, we can compute the coefficients for the complex Fourier series. And then ck is simply ak minus I bk over 2, and c negative k is ak plus I bk over 2. So we can go back and forth between the complex Fourier series and the real Fourier series, and they both can represent the same real value function, and their coefficients are actually very close to each other. Well, this is not a surprise, since it is true for any two bases in general. If you have one basis and another basis, then the coefficients of these two bases can be interrelated. But this relationship is actually quite nice, is that the corresponding functions with the same frequencies from the complex basis and the sines and cosines from the real basis actually fully represent each other. So these two series are almost identical twins, except that the complex series is the only one that can represent complex functions. If you have a real function, you can do it with both. If you have a complex function, you have to use complex series. So this is it for today. Thank you for listening, and I'll see you in the next video.